Hello, everyone. Warm welcome from the Australian National University, and I hope that you are keeping safe and healthy wherever you're joining us today from. My name is Jay, and I look after international relations and partnerships here at the ANU in the areas of sciences, health, and medicine. Joining me today is my colleague Arthur Shu, and of course, our speaker for today, Associate Professor Luke Connell. Before we start, I would like to acknowledge the Ngunnawal and Ngambri people, who are the traditional owners of the land where ANU is located and where we are broadcasting to you today from. And I pay my respects to their elders, past and present. Let me briefly introduce our speaker for today, Associate Professor Luke Connell. Luke is an Associate Professor here at the ANU Research School of Chemistry, and he's also an ANU Future Fellow. He received his PhD at the University of Melbourne and postdoctoral experience as the Sir Keith Murdoch Fellow at the University of California, Santa Barbara. He then returned to University of Melbourne in 2013 as a Vesky Innovation Fellow and a Senior Lecturer before moving his group to here at the ANU in 2017. Luke's research expertise and interest are in the design of advanced polymeric materials for applied systems. He and his group are at the forefront of research when it comes to the development of biomimicry materials using advanced polymer design, self-assembly, and catalysis. Luke's research has been recognized by many awards, such as the ACS Chemical and Engineering News Talented 12, the Grimwade Prize in Industrial Chemistry, the David Syme Research Prize, and he's currently on the editorial board at Molecular Systems Design and Engineering. We are very lucky to have Luke give us a talk today. So without any further delay, I will now hand over to him to tell us about 3D printing of dynamic functional materials. Over to you, Luke, and I'll stop sharing.
Thanks, Jay. I will get my sharing going. Okay, all good, I hope. Great. Okay, so thanks for the introduction, and it's a pleasure to be here and echo Jay's introduction as well, and pay my respects to the Ngunnawal people, and also hopefully everybody is safe and well in this crazy time. So today, so behind me, I guess you can see a little bit of beautiful Canberra here. So this is our backdrop of essentially the campus, the Australian National University campus, and we have the what's called Black Mountain Tower at the back, and Black Mountain. Many people would call this a hill rather than a mountain, potentially. In Australia, we like to call it a mountain. So I've rode my bike home from there today. So I'm actually giving this presentation at home. And just to sort of, I guess, sell Canberra a bit, or tell you a bit about our landscape. I rode home and also passed quite a few kangaroos on the way home as well. So that's sort of where we are in Canberra. It's quite a interesting mix of bush, so nature, and a nice city, small city. So that's Canberra. That's where we are. And so what we're going to talk about today is really 3D printing. I'm just going to get my laser pointer on here, my virtual pointer. So really it's going to talk about how we can, I guess, what the importance or the emergence of 3D printing in society, and also where the challenges are of how we can actually increase its impact. So let me first start off with actually acknowledging the people who do all the hard work in my group. And so here is a picture of my group. It's actually slightly outdated now. This was last August, I believe, or late last year. So we have a little bit of tradition that we try to do our lawn bowling occasionally. So this is down the street from campus, and we have some lawn bowling, which many of you might not know what that is, but it is a bit of fun to do. So this is my group, and in particular today, people who did quite a bit of the work is Jen Zhang here, who's actually moved on from my group here. He's sitting here next to me right there. So he has actually moved on. He's in Queensland now. But there is quite a, this is quite a few people have led to the work that I'll show a bit in a few minutes. And obviously funding agencies, so Australian Research Council, Victorian government, and this Vesky scheme, and also the institutions that I've been involved in in my independent career. So that's the University of Melbourne and now at the Australian National University. Okay, so to sort of get started, I sort of want to paint the picture of how manufacturing looks today, I guess. So traditional manufacturing, this is an image of what you might see in a traditional sort of workshop here. Somebody here making, in this case, some sort of metal structure or metal work. And so the key thing, I'm not going to go into all these details, but a key thing here that I want to highlight is it's usually a subtractive process. So usually you have some sort of slab of material, and then you cut, grind, drill, shape that material, whichever tool you use, to then get the final shapes or final structure of your of whatever you're manufacturing. And so that's a lot of waste. And so if anybody's walked through a workshop like this, you would be just stepping over sort of, granules, fibers, things that have been removed off that slab to then shape that material. So it's not the most efficient process you could have, and in the end quite a wasteful process. So it's very subtractive in general. So that's, I guess, mostly for metals, but this next point here I say is high throughput is expensive to create molds. So I'm a polymer chemist, so in most cases we're not really doing this sort of metal work. We're doing more, injection molding and these types of things for plastic manufacturing. And so that can be very efficient and fast, but you need to get that first mold, or that first die, as we call it, first. That's quite an expensive procedure to get that, just in the perfect dimensions and the perfect ratings for the pressure or whatever that might be. So that first step is quite expensive. So then you want to be able to make sure that's the right design for your system. So that's some again, I'm not going to go into all the details, just painting the picture here for 3D printing. So 3D printing really, I think, changes the way we can design and manufacture materials and objects. So really we're going from a computer image here, so some sort of design, some sort of CAD design, so computer-aided design, and really just taking that design as the input into a printer, and then we can essentially print something out. And so whatever that image is from that CAD file, we can get a physical object from that file. So it's a really fast iterative process, and we'll talk a little bit about the potential and the advantages of this in a few minutes. So this is not necessarily, I wouldn't call this a new technology. So this is this technology of 3D printing has been around for 20 or 30 years, but it's really starting to make a big impact in the last sort of 10 decade. So since probably a patent ran out, is probably the key to that. But it's being used. So there is parts of jet engines that are flying around the world, maybe a little bit less at the moment, but they are flying around the world with 3D printed parts in them right now. So you can imagine, obviously the aviation industry has very stringent requirements on the parts and engineering of their aircraft. So to actually be able to 3D print these things that meets those specifications means that we're getting really high quality printing to be able to do that. So we can see that it's making differences in the aviation industry, but also more broadly in construction. My figure is a bit blurry here, but I hope you can see the idea here. But essentially, there is a large, essentially 3D printing stage here, where you will get some sort of movement of a structure to physically build this house or this construction up layer by layer. And so we're getting, these are becoming implemented. These in different parts of the world are leading this. I just read an article just half an hour ago that Germany has just had their first 3D printed house, but there's other parts of the world that have almost suburbs of printed houses coming up. So it's making a big difference in construction as well. So the other I think, key area and one that interests us is in biology or in human interfaces. So here there is an example of a prosthetic that has been 3D printed here. So we can 3D print sort of prosthetics. You can also think about things that you can print actually that are functional inside the body as well. And so I think probably the most developed and easiest example of that is in dentistry. There is a large movement in various circles of dentists, I guess, that are introducing, so they'll have actually a 3D printer on their side in their offices or in their surgery areas, and they can actually go from an X-ray or some sort of image of a patient and then change that into a 3D printed tooth in that case. So we have this happening to really transform the way people, in that case, for dentistry. But other parts of biology as well, it's starting to make significant impacts in that area as well. I think this is my last sort of broad example, but in clothing in particular, I think there is a lot of opportunities to make innovative types of clothing. Here is an example I quite like here. This is the new Adidas shoes here. So this is a 3D printed sole here. And you can see it's quite an intricate mesh that they have here. So this is Adidas with a partnership with a company called Carbon 3D, which is a US company in the Silicon Valley. And they are expert in printing materials of different softness and hardness and structure. So this foam, they claim, is actually the idea of the design of the geometry of this foam is that if you push down on your foot, the shoe will push you forward. So that's the design of this structure here, is trying to enable people to run faster in this case. And so I think in sportswear in general, I think there is a lot of interesting applications, from things like golf clubs to helmets and to other physical bikes and all sorts of interesting structures. Essentially, if you can think of traditional manufacturing, there is people trying to use 3D printing to change these industries. And so that's some examples on 3D printing and sort of the impact of 3D printing. So I guess some applications of it. So I guess I just wanted to spend a few slides here and be keeping it very sort of overarching and not going into the detail, but just describing a few of the different methods for 3D printing. And there is quite a few different types of 3D printers, and their mechanism is different. And even under each of the categories I will show you, there's probably different, slightly different details in some of these. So I'll keep it quite overarching here. So there's one technique here, which is called powder bed fusion, or also called particle sintering. And so here, this is probably the most common form for metals. So in this case, they will have a layer of essentially particles, or precursor for the metal will be laid down. So essentially a solid dust of metal will be laid down, and then it will be sort of solidified or sintered together, in this case by a laser or some sort of energy source, to then solidify that metal layer by layer. So they will do that, and then they'll add a new layer of powder on top, and then do that again for the next layer, and then repeat that layer by layer. And that's really the key to all types of 3D printing. It's usually done some sort of layer by layer technique. So this is probably the most common for metals. Let's see, that didn't seem to go forward. Yeah, sorry. So the next method is using sort of what we call VAT photopolymerisation, or VAT polymerization method. So this is a very common method for polymers. So in this case, it can work a number of different ways, but here in this case we're showing a stage which is actually stage is actually being lifted up. And here we have a reactive bath of monomers. So here we can start to solidify these monomers by a polymerization reaction initiated by some sort of, again, energy, usually some sort of light. So we can essentially raster this laser across the surface, guided by our digital file, our digital input. And then again, layer by layer, we'll do a layer, it will lift it up a bit more and do the next layer and then the next layer. And again, we can build up these 3D structures from this material. So this is quite a common method for plastic 3D printing or polymer 3D printing. And again, it's probably the most, broadly, one of the most common, I would say, is this third category here, which is, I would call it extrusion-based methods. So this could be an extrusion of a molten thermoplastic polymer where you can heat the polymer coming out of a nozzle. At this nozzle, it flows, and then you can solidify that on that surface and then build up that structure layer by layer. So that's an extrusion-based method for heating a thermoplastic polymer, thermoplastic plastic. So that's probably the most common method for plastic 3D printing. You can also think of a paste type extrusion as well. And for that, in that case, you could use a polymer in that sense as well. So, or a ceramic or a complex mixture of materials to do that. And foods can be printed in that way as well, where you would have some sort of food paste or some sort of paste. Again, you extrude that, and usually the key property of that is a shear thinning like behavior. And so what I mean by that is if you put some shear or some force on it, it will flow. You take the force away and then it will solidify, and then you can do that layer by layer. So think of toothpaste in that case. So if you squeeze your toothpaste out, it flows onto your toothbrush, and then you stop that force, stop that shear, and then you have your paste on your toothbrush. So essentially that's how the extrusion-based method works. So really, I just wanted to go into some of the applications to give you a bit of a picture of how we think about this, and also the methods. And again, I've just gone very broadly over 3 different methods there. There is more methods that we could think about there. So the benefits of 3D printing excuse me for 1 second, the sun is going down here, and I think I need my light on, so 1 moment. I think that is better. I'm getting a bit too dark there, sorry. It's sunset here. So the benefits of 3D printing. So I think the real key benefit, I think you could imagine that quite quickly, is really we can do things that you can't do with a drill or with a traditional subtractive type method to create a structure. So if you look at this sort of, I think it's quite a beautiful, complex 3-dimensional structure here, and you can really do things that you couldn't do before. And so I think the running shoe example that I just talked about is a really perfect example of achieving a function from a 3D printed shape, which you couldn't make before, but now you can make something which actually you can get send a force down and actually get some force going in a different direction. So having really the ability to make these complex designs to actually enable some sort of new function or new material or new property. And I think traditionally what the benefit of 3D printing has really been in this rapid prototyping and be able to make things quickly. So we talked about at the start about injection molding. So you really need to make that mold, which is a very long, expensive process costing thousands of dollars. And so you want to get that right, that design right, before you can then make things very cheaply. But here in this case, in 3D printing, you can actually really be very creative with those designs. And it doesn't matter if you get it wrong the first few times, you can then rapidly iterate to figure out what you want to get to. And so that's really a big advantage. And like I said at the start, less waste, because now we're talking about an additive example rather than a subtractive example. I noticed a question coming up here, so I'll try to answer questions if I notice them coming up. And so we have a question coming in from Anonymous, but it's, are there any biodegradable materials that can be used to 3D print with in place of plastics? And so the answer to that is yes, there is biodegradable materials. So actually one of the more common extrusion-based plastics is called PLA, polylactic acid. So that's a polyester polymer. So that polymer is actually one of the few that is degradable, and it's actually, depending on your definition, they can be compostable as well. And so PLA is a very good material. It has good properties. And so another question just got asked related to that. So with biodegradable material, is the tensile strength similar? And again, so PLA has decent tensile strength. It's not as good as the other most common polymer, which is ABS, which is a copolymer of styrene and other materials to really make it quite a strong material. But there's a lot of research going on to this, and it is definitely something that people are really thinking about in terms of making it high strength and functional, but thinking about the environment. And again, the example of that shoe that I talked about, the company Carbon 3D is really putting that into their design. They're really putting in degradable and end-of-life analysis for these things from the start. Okay, so let me just move on. So there's obviously, if 3D printing was so good, I think everybody would be using it already. So there's obviously some challenges in 3D printing, and some of these are the challenges that I want to talk to you a little bit about what our group has been doing. But in particular, probably the biggest challenge is speed. Again, if you're competing with injection molding, these things can happen in seconds. You can make thousands of bottles or whatever it might be very quickly. A 3D printed structure is layer by layer. So you have to print that first layer and then the next layer and the next layer. So depending on the size of that object, there's always going to be a time. So the bigger the object, the longer the time is generally the case. So there is a trade-off there. So for high throughput manufacturing, that's a challenge. So materials flexibility, there is not as many commercial options for 3D printing. So there is a definite need for further materials, and in particular for functional materials. So high strength, flexible materials, and some examples that I'll talk about today, and self-healing, and actually things that are shape changing, so we can actually control how these things actuate or move on some sort of stimulus. And we actually can call that 4D printing is a term for that. So taking time as the fourth dimension for that. So that brings me on to some to my research. Sorry, I was just trying to look back into the questions. So there's a question here: what is the minimum thickness that we can print in metals? That's a good question. So I think the Z dimension for 3D printing is actually probably the highest resolution of X and Y is related to how slow or how much control you have over the stepper motors, or the things that move the whatever the mechanism is, and the thickness is controlled generally by how you make it. So for metals, it's usually some sort of actually nanoparticle type powder. So it's sort of actually dictated a little bit more from that. So it's actually, probably within, it's in low micron, so micron to tens of microns would be the maximum it would become. And I've got another question from Rudula. Is the nanoparticles incorporated into the polymer? So most polymer-based systems don't have nanoparticles in them, but it's definitely something that can be done. And I didn't talk about printed electronics or anything like that, but a lot of the printed electronics will actually use nanoparticle inks like silver or copper as an ink to actually make some things conductive, and that's more based on sort of inkjet printing. So moving on to, I guess, some of the things I want to talk about today. So we're really trying to print. So I guess my group is really interested in what I would call molecular design. So really looking at the structure of a polymer in particular to then have some sort of function. So looking at molecular scale design and then sort of macro scale function of instilled by that design. So today I'm going to talk about some pH responsive inks. So we can call these inks as 3D printable inks. We'll talk about cryogels or shape changing materials. That slide didn't get updated for some reason. And also we really, at heart, we're a chemistry group. So we're talking about the dynamic covalent chemistry here. So using this shuffling of an imine bond here. Let me move on. So first little part I want to talk about is designing this pH responsive ink. So this polymer here is poly 2 vinyl pyridine, and here this amine, a different pH can be charged, so we can actually create a swellable or deswellable mixture or object. So what we can do actually at higher pH, this will contract, and at lower pH we get the charge and it will actually expand. So we can use this for various applications. So here we're just showing here we can actually control essentially as like a filter, so we can control the flow rate depending on the pH, and we can go from a fast or a slow flow rate from that. And another thing that we did with this system is actually we can use this as a substrate to make a catalysis. So what we did here is we essentially make this polymer in, so I think Milena had to make about 50 or 60 grams of this polymer, and we essentially put it into an extruder. And so we extrude it, essentially this heats it up and slowly extrudes and spits out basically this fiber here. So this is the input for the 3D printer for extrusion-based printing. So this is the thermoplastic style of printing that I mentioned. So this is our own homemade 3D printable ink here, based on this pH responsive unit here. So here's an example of what that filament looks like. So we can control the size of that depending on what the printer wants. And it's important to have sort of quite a smooth material here for the printer. Essentially, we can use a commercial, relatively cheap, less than $1,000 printer here, and we can print different shapes on that based on our CAD file. Here I showed you before about the different flow, so this thing can change its shape based on the pH that it's in, so we can swell or deswell, and that can change the flow rate going out of a system. So here at high pH as a high flow rate, at low pH as a small flow rate, and we can cycle this back and forth as essentially a fun thing to do for this experiment, but it's showing you the concept that we can change its shape and then change its function. In this case here, we have a catalytic object. So this pyridine group can actually be like a ligand, and essentially we can add, in this case, silver salt to this and then reduce that silver salt. And here we actually have like a composite material where we've actually created like a mesh here, So we're trying to get a high surface area, and then we put in a silver embedded into that structure, and then we can use that silver to actually catalyze chemical reactions. And so that's what we did here with this nitrophenol reduction. And we can use that as our catalytically, our 3D printed catalytic objects here. So again, looking at the design of the molecules, the molecular design, and trying to embed function into those materials. You can see here, there's our control reaction, no catalyst. We have our catalytic object. We can get a high conversions quite quickly for our structure. So then we go on to our next question. I'll just check into the questions again. So I've got a question. Is there a particular method better suited to 3D objects on a very large scale, say a house? That's a good question. Yes, I guess. So most of the construction type mechanisms essentially looking at concrete and things that can cure concrete quickly. So again, that's almost more like this paste type extrusion. Obviously, a different sort of level of a different scale of paste. So that is generally what is being used. Yeah, I'll say what the answer to that is. So Partha says how the viscosity will affect the resolution of 2 lines printed by conducting ink per se. So that's a good question. I might actually answer that in a moment with some of our data. So it's very important, the viscosity, and we're about to talk about that. Are certain materials better suited to particular methods of 3D printing? Yes, well, yeah, I guess we're going through that a little bit now. So I think hopefully I can come back to that if you still have that question. Is the catalyst nanoscale? So yeah, so basically that is essentially a nanoparticles embedded into that composite material there that we have. Okay, so the next sort of material that I want to talk about is this dynamic gels. And I think really part of that question is there is a 3D printing space. There's this optimization that we need to think about for this gel printing, and it's really based on rheology. So we would need to figure out what the correct rheology is for it to be able to flow and then to set. So it's really quite important. So critical, I would say. So here is an example. So again, so toothpaste, so squeeze it out and then it stops flowing. And essentially this is what this case is here. And so here we have a paste polymer. In this case, it's actually a lightly cross-linked polymer. And here it is, the key part of this is, well, I'm not going to go into too much detail, but it's actually a dynamically covalently cross-linked. So this imine can reverse, I should have a reverse arrow here. It can reverse back to free amine and free aldehyde. And so this is a really nice thing because then you can actually go from cross-link to decross-link with the chemistry. And obviously you want to do rheology tuning. So that is based on the concentration of the polymer in your solution and also the degree of cross-linking. So how much of this you add. The more you add of this, the stiffer the gel will be and the harder it will be to flow. So you need to have a certain space where you can do this. And so these are the nice part about this dynamic covalent chemistry is actually this is self-healing now. So this chemistry is always dynamic. So we can cut it and break it up and stick it back together, and the chemistry will reheal those cracks or breaks in the material. So this gets onto the rheology tuning of this material and also the self-healing. So you need to have, well, I guess this is actually probably more about self-healing, sorry, but we're using the rheometer to look at this. So we, I think this figure shows it probably the best, where basically you shearing the rheometer, so putting a lot of shear on this, and then we essentially put as much shear as we can until it actually breaks. The network is breaking here. And then what we do is actually just let it sit on the rheometer, and then after a certain time it's recovered, and we can then remeasure these materials. So we essentially break it by shear on the actual instrument. And you can see here, we get pretty good recovery very quickly. So this is minutes. So we can actually get almost 100% of our recovery, our materials properties back very quickly. And so that's really key for something that can break and reform these bonds quickly. So this gets to this tuning of rheology. So we're tuning the cross-linker ratio, we're tuning the composition, and these green dots here is where we can actually form a soft and extrudable gel, which is sort of our criteria for 3D printing. And so we can do some more rheological analysis on this. So we have this depending, essentially on the storage modulus we're relating this to, and how that fits into this 3D printing space. And yeah, so this is the apparent viscosity here as well. So this is the 3D printer in action here. So here we are printing a butterfly from our CAD file, from our computer file. And here we are putting a layer of our ink down onto this. So this is a self-healing printed butterfly. So if we can chop this butterfly's wings off, we could stick it back together and it will heal its wings. Unfortunately, we can't make it fly just yet, so that's something that we would like to be able to do, make things even move after this as well. So here's another example of this self-healing. So we can print our multi-layered star here, and we can cut it, and then we can stick it back together, and it can heal and it gets its properties back. So this gets to this one of the questions before. What are the different polymers or materials for printing? So each of the different methods has its drawbacks and its advantages. This paste-like material, obviously, it's harder to get really high resolution with this paste printing, because essentially this is like a toothpaste. It depends on the size of that needle that you're using. So that can be a disadvantage if you want high resolution. So we've taken this a little bit further here. So this is a network here where we have two networks. And so here we have our dynamic covalent bonding here, where we can react this aldehyde with this hydroxylamine in this case, and this aldehyde here as well. And we also have these boronic acids here as well. So we can form a first network here through our imine chemistry. We have a certain property here. So we have a gel. It's a fairly soft gel. What we can do is actually cross-link a second time with this different network, and we can have a second dynamic cross-link. And so these boronic acids are also a dynamic covalent chemistry, so this can reverse back as well. And so if we can reverse that by adding a catechol into this system, we can go back to its original properties. So we have a network, we cross-link that network and makes it harder. So it goes from this red line, red dots, to the blue. So it goes from soft to hard, and then we can break that second network with the catechol, and it goes back to soft again here. So just again, sort of just an example of playing with this material's properties. So we can change the material's properties by this molecular design. The other nice thing about this structure, I'm not going to go into too much detail here, but I'll just go to the cartoon here. What we can do is actually, these boronic acids can actually interact with carbohydrates on the surfaces of cells, and we can actually capture cells onto our object, and then we can actually release cells as well. So we can actually use it as a cell capture and release assay, and we've done that with in this paper here. I'm not going to go into the details, but we can actually do this with cancer cells. So this type of cancer cell here, we can actually selectively bind these cancer cells. This is a collaboration, and I'm not going to go into too much details. And I think I want to stick to the 3D printing stuff. And looking at the time, I want to keep moving. So an important part of our design has actually been to create porosity in these materials. So if we've been able to create porous materials, we can then change the properties. So here we use ice crystals to actually freeze ice inside our structure and then thaw it under high vacuum, and we get some porosity into our structures. And you can see here, different cycles of that method of freezing and thawing, we can actually increase here's the G prime. So essentially you can think this as strength. So with each cycle of that, we're actually increasing the strength of this material. And in particular at minus 10 degrees, we can get really interesting properties here. So we're getting significantly increased strength of these materials by creating these porosity or porous structures. So this is, yes, this is another example of what this looks like. This is a confocal microscope image. We have a printed gel. We can then freeze thaw it, so create this porous structure either at minus 10 or minus 20, and we can see the different structures here. And so that leads me into sort of this whole area we're quite interested in is really creating high strength materials. So we do a lot of mechanical testing of some of our materials. So we look at essentially what's called a stress strain curve. So a strength strain curve. Essentially you have your polymer and you stretch it slowly and you measure the force that it takes to do that. And you get this material, you get this plot here, and we can get some various parameters of our materials from that. This is an example of a material we've made, and you can actually stretch this thing, in this case, over 7,000%. And this is actually, we think we can go further, but we could actually, the machine can't actually go any further itself. So we've got to the limits of the machine that we have at our disposal. We can also create these things at high strength. So here we have a object here, or a material we have here, and we can actually hold up, a kilogram weight. I think this material is 100 milligrams, and we can pick something up that is 1 kilogram. It has good recovery properties as well. We press it down, it will come back. And here there's these materials, these high strength materials. So these, we do this. This is the data we get from this stretching example. Depending on the molecular design. So here we've got a cross-link density. We have changed the cross-link density, and we can increase our strength here. So these are self-healing as well. So we can cut these, stick these back together and self-heal them. And I don't want to go into too much on that. That's some details. I want to move on to this part. And this is sort of this idea of changing shape with some sort of stimulus. So these materials, we can design them in a bilayer structure, where one layer is non-responsive, the top layer is responsive, and essentially we can put these into we can make these temperature responsive. So at 50 degrees, this will curl up, change shape, and then it will reverse back at 25 degrees. And here is a little video of us doing that. This is Jen holding this object here, and then it will curl up at 50 degrees, almost instantly, within seconds. This curls up like this. And we can really use this because of our self-healing properties. We can essentially make lots of different structures. We can stick them together and make different objects, and we can design in the way these can fold or change shape. So here we can make this sort of twisted structure. We can make this, I'll look at this and see a bird structure here, as my 5-year-old would draw it, probably as I would draw it as well. And here we're trying to make a box here. So we can try to make this from a flat structure to then fold up into a box. We can also make these things do work. So this can actually physically lift things. So here we have an object that can do physical work by this shape change. It can go up, lift this weight, which is 15 times the weight of this material here. We can do physical work and sort of keep on doing physical work. I don't want to go into too much detail here, but we really look at the design, so how we can use chemistry to change the properties. So I've shown you using covalent chemistry. We're also interested in ionic or ion coordination, metal ion coordination, and also in hydrogen bonding. So here we're using this ion complex to actually increase strength again. And again, we can change that stoichiometry of the ion in the system, and get a more high strength material. The nice part about this one is actually it's humidity responsive now, not temperature responsive, but humidity responsive. So I've got a little video here. So is it playing? Maybe it doesn't want to play. I go off the pointer. So here we're blowing dry air at it, and then in a few seconds we start blowing wet air. There we are there, and the wet air, so the humid air, will make this respond. So the first part we're drying, this is blowing air right now, the same flow rate, but dry air, no humidity. We switch it to humid air and we can essentially change shape with these things. So we have a lot of fun with this. And we can make sure that we can do all these different things with this. In essence of time, I might not go into all the details, but we can use this actuation to lift objects, to close and open circuits, and also for enzyme immobilization in this case here as well. So this is the 3D printing of that material. Got some sound here, I'm sure everyone can hear that. You don't need to hear that. So this is the 3D printing of this. And so we can, again, use this the ability to print things to then control the shape of this. So the key part of this is a different layer thickness won't be responsive as thinner layers. So we can control the thickness either by sticking them back together or printing them, or printing this object here, where you can have this sort of flower shape, where we can print flower structures. So here is the printing going on up here. So this is my last slide, and I'll get to some, I know the questions have been popping in, I'll get to them in a moment. So this is really the key to this story, I guess, or what we're trying to do is really use molecular design to enable new functions for printable inks. So we can make strong self-healing materials, we can change the shape of these materials, and we can also make functional materials here. And so that's where I'll wrap up today, apart from a little advertisement, I guess, for a new master's that we're going to start next year in materials at ANU, and in particular in chemistry. And there is a course that will have, part of that course will dive quite deeply into additive manufacturing and 3D printing in particular. Okay, so let me try to get some to these questions now. Okay, so we've got a question. Can we print viscoelastic material for a cardiovascular implant, like aortic valves? Will the 3D printed implant be able to withstand cyclic loads? Does your group in developing materials with high cyclic loads? Yes, so absolutely. So I think this is a really interesting area for, and so there's lots of challenges there. I think even just the challenge of a cyclic load and unloading, and there is some really nice work coming out of various places in that, and we are interested in this, and maybe not so much in the 3D printing part of it, but just the fundamentals of loading, understanding loads on hydrogels in particular, because it needs to be a hydrogel type material for bodies. So it is we are looking at that sort of thing, and we're coming from the angle of understanding the cyclic loads first and then trying to 3D print those things afterwards. But I think the answer is that we can. I think these things will happen in the future. I think it will sort of change the way we think about implants in that case. Okay, we've got another question. So for which type of plastic can resist high heat? Yeah, so I think all plastics have a different thermal properties. So depending on what you want to have, but at the same time, all plastics will degrade. So they're not necessarily high heat responsive, but so if you go to 400 degrees Celsius, most plastics will be degrading there. But ABS, I would guess, is probably the most common printed polymer with the highest heat resistance. But you can design that. You can design that into your to your material. So we have the question, how does porosity increase the strength of the material? Won't the structural integrity become lesser? Yeah, so that's a good question. That wasn't something that we were actually expecting necessarily, but it's the key is it's not actually the hydrogen bonding. Sorry, it's not actually the porosity that's increasing the strength. It's, which I sort of jumped over that. It's actually the hydrogen bonding. So when you decrease the temperature of it, you're actually starting to form these crystallites in the material, and you get these hydrogen bonding parts of the material sort of essentially gluing together. And it's that strong hydrogen bonding that's caused by the ice and freeze thawing, the crystallization almost of that material. That's what's actually giving it the high strength. So what are some applications for shape-changing printed objects, say in biomedical science or healthcare? Yeah, so that's a great question. I think sometimes I feel like some of these materials are not, it's almost sci-fi sort of material, science fiction type material, but I think there is emerging applications here. So I think in particular for like sort of soft robots, autonomous robots and things like this, I think there is potential to be able to use these materials to do that. There is some really nice work out of MIT, I think, you know, essentially where there is a shape-changing material that can sort of actually guide its way through an artery or a vein, and can actually do that by changing its shape to do that. And so it's like a surgery application in that sense there. So I think we're just scratching the surface in potential applications here. So I think I think a lot will happen in the next decade in this area. Okay, so if there's any other questions, I'm not sure if I've missed any questions here. Is machining possible for 3D printed objects? I'm not sure if I quite understand that question. I'm not sure if you mean if you can actually then process an object. So I think if that's the question, I think yes, you can print something and then do further processing steps to something afterwards. I think that is depending on your material, that is definitely a potential. And in many cases, in particular for the photopolymerisation, what they usually do is have a two-step procedure where they'll lightly cross-link something and then actually take it to another process and actually cross-link it more. So do a second step of cross-linking. That's like a hardening step. So actually to increase the properties of that. Looking for more questions here. I'm not sure if I've missed.
Keep going through them, Luke.
Yeah, I think I've covered them now, Jay. Is that right? Like I can...
Yep. From what I can see, I think you've answered all of them. Fantastic. Look, if those attending, if you have other questions, please put them through the Q&A box now. We've got a couple of minutes left, otherwise we may be finishing on time.
Yeah, cool. Yeah, it's always hard on Zoom calls with questions. You got to sort of like talk slowly in case somebody starts to ask a question. And we've got one come in. So can we prepare non-corrosive and durable implant materials from this method? Yes, I would say. Like, again, so I think it's all in materials design. I think any real property that you want, I don't think it's a matter of then just going to the piece of paper and designing that material, and then there's a challenge of making it printable as well. But I don't think there's not many things that I would say we can't do if we actually, if you put the infrastructure and the effort into it. I'm sure we can do that. Okay, well, this is a different one. Can we print entire embryo with 3D printing in the near future? So that's an interesting one. Maybe. I haven't put my brain into that. I'm not sure if I really want to put my brain onto that one. But it's an interesting question. I think I think the complexity is getting to very complex. I'm not sure if it's getting to quite that complex yet. But I think designing micro environments with 3D printers, I think, is definitely something that people are doing. There's actually a company in Sydney, Australia, not printing embryos, but they are printing 3D models for biology. So they're actually printing models so they can actually create environments that are like the body, and then you can study the cells, how they grow in those environments. So they're not printing embryos, but they are printing sort of different types of environments of different cells. Okay, another one come through. What are the desirable properties criteria for a material to be considered printable? Yeah, so I think it's sort of a hard one to answer, but I think it depends on your method of printing. So each of the different methods have their own requirements. So obviously, if it's photopolymerisation, you need to be reactive with light, and then if you've got that, then you can do lots of different things. For extrusion-based thermoplastic, it needs to be meltable. It needs to have a TG, so you need to have a glass transition temperature. So you need to be able to heat it up, and then it flows, and that's important. And obviously, the viscosity of the paste ones are important as well. So it's a balance of different things there. Okay, we've got some more coming through. It's good. So we've got making mold is tough in conventional methods. 3D printing is time-consuming for mass production. Do we have hybrid techniques that combine precision of 3D printing and the speed of injection mold methods? Yes, so I have seen examples of people 3D printing for injection molding. It's challenged because you need quite high strength material, but you could 3D print metals to make a mold, and so combine those two methods. So I think absolutely. So I think there is ways to integrate 3D printing into traditional methods. It doesn't necessarily need to be traditional versus 3D printing. I totally agree. I think there's good ways to actually combine different methods. What are your thoughts on use of 3D printed objects in rockets and other space applications? Yes, I think that's great. I think there is definitely scope here for that, and so my group is interested in that, I would say. So in particular I didn't really talk about electronics, but we're interested in printing electronics, and so we're interested to print electronics. We're interested even to print 3D electronics in space, if you could do that as well, so you could actually have manufacturing in space. So there's lots of different opportunities, I think, and I think that's only going to increase. Can a completely functional heart be 3D printed? Yeah, I'm not sure. If yes, how efficient will it be? Yeah, it's an interesting one. I think, I can't say that we're close to that sort of thing yet, I don't think. But I think there is scope to print different types of materials for the body. So we're quite interested in making these high strength materials, and particularly for something like a cartilage or a ligament. If you could 3D print a ligament for somebody for a knee, I think that's pretty close. I think for the heart, that's lots of challenges for that. And how viable are 3D printed organs? Yeah, again, so I think that's a similar question. It's hard to say. It depends on the organ. I think people are printing like skin, artificial skins and things like that. So that is quite developed and quite viable and efficient. So it's useful. Obviously, the more complex tasks that that's more of a barrier. But you need things to actually be functional and doing other things. It's a whole set of challenges.
Great. I think we're on time, Luke.
Good.
can I just, on behalf of everyone, thank you for that informative talk, for giving us a glimpse of, all the work that's going on in your research, your group's research. For all those attending, thank you for coming along. Thank you for those questions. If you're interested in the work that Luke and his group are doing, I'm sure you can find their group on the ANU website. If you're interested in joining, becoming part of that research or studying further here, you can see, the name of the master's degree over there. If you indicated you're interested in learning more about postgraduate programs here, we will be in touch with you about that. Thank you for coming along and enjoy the rest of your day. And we've got a few more talks coming for the rest of this month and in July. So if you haven't registered, please do, and I'll see you there. And Luke, thank you once again.
Thank you. Thanks, everyone.
All right. Bye-bye.
Bye.